So another new video, this one also about calculating P. This time we're using a slightly different system based on random numbers. As you can see, we can generate random numbers and assign to these random numbers the meaning of x and y coordinates of points. To fix ideas, let's consider a circle with a radius of 1 and generate here. So these random numbers in the interval 0 to 1. For each point, we generate two random numbers. To one, we give the meaning of x, and to the other, the meaning of y. So basically, when we have generated a pair of random numbers, we have practically generated a point whose coordinates can range from 0 to 1. Now, what can happen? Let's introduce a Cartesian coordinate system. If the point falls inside the circle, how do we notice it? Well, let's jump straight ahead. Let's go to this line. The coordinate, the sum of with the Pythagorean theorem, we can see that the sum of the squares of the coordinates must be less than 1. There would be the square root, but in this case, it's not important, because if we chose 1 as the radius, we can also consider that the square root of 1 is 1, and therefore we can also remove the square root. And this is interesting to make the calculation faster. So if this condition is verified, we have a point that falls inside the circle. If, on the other hand, this condition is not met, meaning the square root of the sum of the squares of the points of the coordinates is greater than 1, then the point will fall outside, okay? We can therefore generate a very large number of points by using random variables to determine their coordinates. Then, we can carefully count exactly how many of these randomly generated points happen to fall inside the area of the unit circle. If we do this, based on the property of random numbers where the distribution is uniform, there are no points more dense inside the circle compared to those outside the circle. Then we can compare the areas by comparing the number of points we generated inside the circle and outside the circle. Let's say inside the circle and in the entire square. So let's reason about this. The area of the circle is pi r squared over 4, because I am considering only the first quadrant, so the part of the circle that falls only in the first quadrant, because we are generating points with coordinates minimum 0, maximum 1. The area of the square that falls in the first quadrant is r squared. So what will the ratio between the two areas be? Pi divided by 4. Now, this same ratio is equal to the ratio between the number of points that fall inside the circle, and we can count this with a counter c. If this condition is met, the point falls within the circle. We increment the counter c. Compared to what? To the total number of points we have generated, and we will call this n. So at a certain point, we have that the ratio pi over 4 is equal to the ratio c divided by n. From this, we can also derive pi and see what the value of pi will be. Now, to do this, we obviously need, I've already run the program here. We need to go back to the code. We need to build a code. I've already done it. Wait a second. Here it is. This code does the things I told you about earlier. That is, it imports the random number library, the random number module. It initializes a counter to 0, defines 10,000 steps, because we clearly should try to do an infinite number of points. We can't do that, but we'll settle for an approximation with a large number of points. Then we go into the range. We start from 1 because I also have to do a division. And then we calculate, we assign the x coordinate, the y coordinate. This was a print statement for checking to see if it worked. And then if the square root, well, there's no square root here. If the square of x and the square of y added together give a number less than 1, it means that the point falls inside the circle, and so I trigger the counter. At this point, we print the results, where clearly the number of points generated up to that moment is given by the variable I, and the number of points that have fallen inside the circle up to that moment is given by the variable c. The 4 point is needed because we had to multiply by 4, and we put a 4 point so that our expression becomes a real valued expression, and so we must we must perform this conversion. One of the ways is this one here. Once this is done, we can run the program and let it run as we go. We can follow it, even if it's a bit difficult to follow. Maybe we'll let it run for a little bit. We see that it converges towards a value that is around 3. Let's wait. We are still at 3,000, 4,000, etc., etc. I set it to 10,000 steps, so it wouldn't be too long. In the meantime, we will see that there will be a good convergence towards the value of pi. It must be said that there would also be the possibility of using other modules of the random library, in particular the uniform module, which gives us an even better result. There you see, even at the end, we managed to get 3.11. It's not an amazing approximation. In the other video, we had obtained more precise results. However, this method too, especially from a, let's say, a computer science point of view, to understand the utility, let's say, of random numbers, is certainly very valid. All right. Best regards. See you next time.